Stepping forward and stepping backwards. So the main objectives, we want to understand the difference between source step in, forward stepping, and step out, backward stepping treatment systems, and understand the implication of applicator curvature of source position inside the applicator. So that's the main thing. There's not too much difference in a lot of your applicators, but applicators with large curvature, in particular rings, there's a really big issue that needs to be overcome, and it's handled differently with stepping forward or backward stepping systems. And so even if you don't have a ring system now, you might get one in the future, in the near future. So it's a really important lesson. So you've got a Varian, a Babig, Eckert, and Ziegler afterloader. What does that mean? So these HDR systems use backward stepping source movements. This means that the source starts at the distal end of the applicator and steps backwards towards the afterloader. Okay, so it's an important thing. And for nucleotron Electa HDR afterloaders, it's the opposite. They're forward stepping. This means that the source starts at the proximal end of the applicator, closest to the afterloader, and steps forward towards the tip of the applicator. And we'll see throughout the presentation how there are big differences in how the two are handled with big curvature in applicators like rings. So why does it matter? In general, it doesn't, except when you have an applicator with a large curvature, example, ring-style applicator. So here we've got a number of pictures of ring applicators. There's some tandems, which it doesn't really affect that much, but these rings and different rings will behave differently. So in most applicators, the source travels along the central path inside of the applicator, and step sizes are equal, right? So if we put in a 2.5, 3 millimeter step size, every time you move it, it moves 2.5 or 3 millimeters, right? That step size is equal along the whole path. It doesn't matter whether the source is forward stepping like Electa or backward stepping like Varian or Babig, Eckert. Why is the ring different? In a ring applicator, the source does not travel. In a ring applicator, the source does not travel along the central path, nor are step sizes equal. This is due to a few reasons. The inner lumen of the ring applicator is wider than usual to enable the source and cable to move easily through the applicator without causing an obstruction interlock. Friction between the source cable, and inner lumen differs in different parts of the ring. Tension on the source cable changes as the source moves around the ring. In a ring applicator, variation in source position also depends on the source stepping motion, forward or backwards. We'll talk about more details shortly. So let's talk about backward stepping sources. So again, these are your Varian or Babig, Eckert, and Ziegler. The source is driven all the way to the end of the ring. As the source is retracted, coming backwards for treatment, the source cable straightens and tightens the wire over the first few millimeters of retraction, and the source does not actually move. Once the source cable is tight around that inner portion of the ring, the source starts to move and the stepping motion is uniform. This can be corrected for by defining the end of the ring channel beyond the real end by X millimeters and using the first activated source position X millimeters proximal than the most distal available dwell position. The exact amount is determined during commissioning, and this position is equal to the source position at which any subsequent proximal source positions move backwards by the step size length. So again, the first few positions are variable, and then at a certain point, it tightens around the ring and then just pulls back with uniform step positions. And that would be equal to that X millimeters where we've moved beyond the real lumen for reconstruction, and our first activated dwell position is that same X millimeters proximal. And a little confusing, hopefully some of these next few slides will clarify that a little bit better after a quick introduction to forward stepping sources. So forward stepping sources, Electa and nucleotron. As the source steps forward in the ring, it travels in a straight line until it hits the side of the lumen. It then slides along the outer edge of the lumen as it moves around the ring. About halfway around the ring, the inflection point at which the source needs to change direction, sort of going forward and then coming back along that ring, the source cable kicks out, causing the source to move very little over several source steps. The source is then pushed by the cable around the outer edge of the lumen to its most distal dwell position. I know there are probably a number of questions so far, but we'll have a lot of pictures coming up. So hopefully these pictures will help explain things in much greater detail than my explanation right now. An additional issue with ring applicators. We cannot typically see the tip of the channel or lumen on ring applicators, and it can make commissioning more complicated. So lots of times we must be able to relate inner geometry to outer geometry. You can do this in a couple ways. If you've got model files in your TPS, you can look at the outer geometry versus inner geometry, or you can just go by the manuals provided by the vendor and actually looking at measurements from the outer geometry and how that correlates to where the source should be on the inside. Again, more details and pictures to come. So let's look at backward stepping systems. And take note that in these backward stepping systems, a lot of the processes that I'll describe in terms of how to commission it or how to visualize it, how to measure it, a lot of those processes can be applied to forward stepping systems. Just the mechanisms for correction are slightly different, but the measurement techniques can be utilized on both systems. So let's talk about backward stepping systems. Backward stepping source motion. So this happens to be a Gammamed IX example. So your rings could be different, your machine could be different, but we're talking about the mechanism of the behavior. So in this case, the source moves, I don't know if you can see my mouse, but it comes all the way out, moves all the way around the ring, and goes all the way to here. Okay, this is at 1300 millimeters. Here's at 1295 millimeters. If you look at it, it's barely changed position, maybe 1 millimeter. So we've moved back supposedly 5 millimeters from 1300 to 1295. But if you can look at where the source position is here, right at the red line, and here it's about 1 millimeter behind the red line. So in a 5 millimeter difference in dwell position, the source has only moved about 1 millimeter. And that's because it's bowed out around the edges here. And in that first 5 millimeters, it mostly just tightens. You can see it's tightened a little bit here, and it doesn't really pull back. Then in the subsequent dwell positions, it's already tight, and then it pulls back 5 millimeters at a time. Now you can see a big difference, about 5 millimeters from here to here. Another 5 millimeter dwell position, it actually moves about 5 millimeters. And again, the same thing. But the key is this, where those green arrows are between 1300 and 1295 in the system that I commissioned, it only moved about 1 millimeter. So you've got a variable step size. Over your first 5 millimeters of dwell positions, it's only moved about 1 millimeter. The subsequent dwell positions, it moves approximately 5 millimeters per step in equal step sizes. So that's important. So we can't use those first dwell positions where there's variable step size, because your afterloader, your TPS, you can't program in variable step size. It only moves in your TPS by fixed step sizes. Here's another diagram, just a picture I drew. So here's the source, the red one is the source in my Gammamed at 1300. You can see it comes in and goes sort of around the outside, and the source ends up right here. Well, the blue one, I've just pulled it back 5 millimeters. Well, what happens? You got all this gap, all this space here. The first thing it does is just tightens around the ring when you pull. Well, all that motion just tightened it, but it didn't really move the source back very much. And then subsequently, every 5 millimeter step size, it's already tight, so it just moves the source 5 millimeters back, 5 millimeters back, 5 millimeters back. But that first one, where those first few dwell positions over the first, say, 3 to 6 millimeters, they're really just tightening the wire around the ring and not really moving the source. So that's the main mechanism for backward stepping motion. So 5 millimeter step size, yet small move in source positioning. And then it moves subsequently 5 millimeters fixed step sizes from then on. Is this the same for all ring applicators and afterloaders? The exact motion of the source is dependent on ring size, so the diameter of the circular path in which the source travels, say a 26 or a 30 millimeter ring, physical properties, the inner lumen diameter, so how much room is there for the source cable to move around, how much room is there for to tighten. Properties of the cable wire, how far around the ring is the source traveling. So I've worked with, say, a Venezia, where the source just travels a half arc or a half circle, and the effect isn't that much. Or I've used a Gammamed ring where it travels over 360 degrees, and it's probably the most exaggerated. So it behaves differently in different rings, and that's why we commission these. So again, here's an example of a Varisource, which is a little bit less than 360 degrees. It's titanium. And here's an example of a plastic Gammamed applicator, where the source travels around over 360 degrees inside the ring. Just two examples. Before I get into how we commission that, does anyone have any questions or need clarification on the principles of why you've got variable step source at the beginning and then consistent step sources after that?
If anyone has any questions, they can feel free to unmute themselves.
Okay. If not, you can still send a message in the chat and we can come back to it in a little bit.
Absolutely.
And we'll get to the how do we commission this. So many times you cannot see the end of the channel, the end of the inner lumen on rings. So we must be able to relate inner geometry to outer geometry. One option is if you've got solid model applicator files, you can get these through most vendors, maybe not all, but if you have that option, it's really handy. So you can overlay, say, an applicator file, my applicator file. If you look closely, I've got these little purple blocks. This represents where the different source positions are in my TPS. And then I can look at my source position on my X-ray, for example, and I can compare the two. Where is my TPS saying it's supposed to be? And where is my actual source position? And I can look at that difference. So that's a really easy way to do it. If you don't have solid model applicator files in your TPS, another way is just ask the vendor for detailed schematics. It's really easy. So you can look at, for example, if you specify the handle of the ring right here as 12 o'clock, then the vendor can specify the nominal position of all the dwell positions as an angle from the center of the ring. So let's look at this one, going with the letter A here. So if we specify this as 12 o'clock, then the vendor can specify what angle are the nominal dwell positions for this particular applicator. So there are lots of different ways. You just need to know the physical properties, and the vendor can supply where those dwell positions are. Or if you've got model files, you can overlay it directly. Or you can even use these model files and find out the angles. So on this model file, for example, I can say the angle between here and the first dwell position is X degrees. The angle between here and the second dwell position is Y degrees, and so forth. So different methods where you can get exactly where the position should be physically within your TPS, and then where they actually are during measurement. So that's the big thing to understand.
Sorry, I just wanted to take a question, or not take a question, make sure there wasn't a question because someone had unmuted themselves, so we can just take a moment.
Sure.
And if they didn't have a question, I did have a question about that, about the nominal dwell positions. And I think in my understanding, you can specify where those dwell positions are. So when the vendor gives that to you, is that like the minimum step size or?
Yeah, good question. So again, different vendors handle this differently. So Varian, for example, will give you equal step sizes. And that's correct, Tim. So you can change this. So in this case, I think I've got 5mm step sizes from center of source to center of the next. I could do 3mm step sizes in Gammamed. I could do 1 cm step sizes in Gammamed, but it will always be exactly 1 cm between, or in this case, 5mm between center of source to center of source. Nucleotron or Electa, their model files will have exactly where the sources will be in a ring, so they may not be equivalent step sizes in an Electa Nucleotron model. We'll get to that a little bit later, but the point is, however you've put in your model file, it will show you exactly where your dwell positions are in your TPS, and you just want to relate where they are in the TPS to where they actually are delivered. And sometimes you'll find differences, and we need to relate those differences somehow in commissioning and apply those differences in actual treatment planning. And the application of those differences we'll get to later on. So I won't go over that explanation now, but that's the biggest thing. You need to know where they are in the TPS and then relate those same distances to where they are physically. And that's how you'll commission those differences.
Thank you.
Yep. And Tim, you know how to get rid of these annotations. Let's see. There we go. Yeah. Sorry. Mouse. Okay. So there are two methods. There are two methods of commissioning. And I always suggest in almost anything I do in physics to do two different methods of measurement and see that they agree. I think that's a really good concept. So even if I'm doing something like small field dosimetry, I might use a micro ionization chamber and an unshielded diode, apply two different correction factors and get the same result, right? You want two methods of measurement is always ideal in order to confirm that what you're doing is correct. So if you have the possibility to do autoradiographs and x-ray the dummy, do them both and see that they agree with each other. It's always good practice in physics. So method one, autoradiograph. Now, I'd like to note that some applicators, this will be more difficult. So for example, again, here's a variance system. It works pretty well. The actual ring dimensions, it's a little bit thinner. I've done this with the Venezia applicator through electronucleotron. It's much thicker, so the dwell positions appear much bigger and a little bit more difficult to find in the center. So it could be easier or more difficult with different systems, but the concept is still the same. So you will need to know the ring outer and inner geometry. So one method is like this, where I've actually drawn based on vendor manuals and on my actual ring exactly where things are. So I know, for example, this angle between this little notch and this little notch, I know this distance, and I can center it perfectly and then tape it down. Another option would be to tape the whole applicator down. Like Sanja taught us a few lessons ago, we can use about 300 MUs from an electron beam. You can get a pretty good image of this applicator on here. Probably what I would suggest over drawing. Use an electron beam, 300 MUs, doesn't matter what energy, and about 100 SSD, and you'll get a really good image of this plastic applicator. You might even be able to see the inner lumen. Careful consideration must be taken taking the ring to the film to ensure proper alignment and rotation. You don't have to worry about that as much if you're using an electron beam to image it. Small errors quickly become big in brachytherapy. Okay, so this is one example. A quick note on transfer tubes. Ensure the transfer tube is as straight as possible during commissioning, as large bends in the transfer tube can have an impact on the distance the source travels into the applicator. This is important for all applicators, not just rings. We do this for commissioning, so do it for the treatments as well. A quick slide that just shows this. Here's a straight transfer tube, and it progressively gets more and more bent. And you can see the source position actually changes significantly if you've got your transfer tubes too bent. So keep them as straight as possible for commissioning. If you commission it that way, keep them as straight as possible for patient treatments as well. Just a little note. So autoradiographs. So here's an example of autoradiographs. Some of these lines, this cross, and this line, and this angular line that shows me how to actually place the applicator. And the rest of these lines, here's one, here's one, here's one, here's one, here's one. They're splitting these dwell positions. And so I can take a measurement and know exactly what that angle is. Well, we've already either from the vendor gotten what these angles are, or from our TPS model file, applicator files, we can measure exactly what these angles are. And we can quickly see the difference between my measured angle and what the TPS model file or what the vendor manual says that angle should be. And we can see, hence, the difference in delivered source position relative to TPS source position. I always run it twice, so I don't just do one film. Here's this particular ring model. I've run number one, run number two, and see that they agree. Here's another type of ring, and I've done one run and a second run for it, just to compare and make sure that we've got the I get the same results both times. Again, good practice in medical physics. Reduce uncertainties in alignment and to ensure systematic motion of the source. Okay, so you run it twice. Again, here's a quick diagram that shows again what I'm talking about, but in picture form. So here's our ring, and either through our model file or through a vendor manual, we've got this angle in red, which shows where the TPS says the source should be. Says the source should be right here with this angle, alpha. Our measured is in blue. We've measured with that straight line through the source position. We've measured this blue theta. So the difference in the two is theta minus alpha. This is the difference in the two angles of measured versus TPS or a manufacturer manual. If the angles are in radians, the arc length S is this actual distance and length. Arc length S equals R times the difference of theta minus alpha. Okay, and R is just the radius to the actual path length of the source. So that would be right in the middle of your ring. So pretty easy, S equals R times, I've actually forgotten what this is called, this Greek letter, apologies. So the distance difference in position is simply delta S equals R times theta minus alpha. Repeat this for dwell positions every 5 millimeters around the usable portion of the ring. And then we can just use a simple Excel sheet to give us these answers. So here we go. I've got the degrees that I've measured on the film. I've got the TPS expected degrees that I got from my model applicator file, or you can get this from your vendor. You say to your vendor, I've got these dwell positions. What are the angles relative to something, however you're doing the measurement, and you can get these angles. And so now I've got the arc length on the film by that simple equation, the arc length in TPS, a simple subtraction of the two, and I've got film minus TPS. So you can see I've got offsets of minus 4.3, minus 6.8, minus 4.3, and so on, averaging out around the entire ring. It averages out to be about minus 5.4 millimeters. I did it a second time, repeated it. I got some slight differences in individual measurements, but overall I got the same average, minus 5.4. So I think I did a really good job measuring this. I got the same results. So I apply this I apply about a minus 5 millimeter correction factor. And again, I'll show you shortly how we apply that correction factor in terms of actual planning. But this is the difference between the average difference between the sources measured and the sources in the TPS. And again, just make sure that you specify the direction of that difference and where those angles come from. So autoradiographs, using your angular measurements, you can directly determine each dwell position and offset in the TPS. So here's a dwell position, and you go to the center of the source. You can see exactly what that offset is supposed to be. So X-ray of dummy source. So you won't be able to X-ray your active source because your active source has so much dose that it's delivering, so many photons. So it's going to saturate your detector. So if you try to take an X-ray of your actual source, it's just going to saturate your detector. You're not going to be able to see source position. So the only way is to use the dummy source as a surrogate. If possible, take an X-ray of the dummy source. You can use a portable X-ray device from radiology rather than a marker wire that you might use for simulation. So the dummy source uses the same cable drive as the active source, so it will behave the same as it moves through the ring. A marker wire will not do this. Now, most HDR units allow you to drive the dummy wire to a particular dwell position. Ask your vendor or ask RCC experts how to do this. So for example, I know how to do this in a variant Gammamed IX system, and I know how to do it in a nucleotron microselection system. You can drive the dummy source to exact known distances in both systems. And most systems should allow you to do it, so ask your vendor or ask RCC if you don't know how. And then just borrow a portable X-ray, a C-arm, something like that from diagnostic imaging. Usually someone would be happy to help you take a few images for about an hour or so. Use radiographic film or digital radiograph. It's another option. Or radiochromic film if your HDR system is in the same room as your LINAC. You can still use this 300 MUs of electrons to take an image. If your HDR room is not with your LINAC, it's pretty tough to use radiographic film with X-rays, but you can still try. So X-ray dummy source. Again, this is a Gammamed IX Plus example. Use the concepts being taught, but again, don't use the exact distances or measurements that I tell you, because they may be different on your system, but the principles of what I'm teaching are the same. So that's an important thing. So use the dummy source to model the active source. So measure the dwell positions of both in your QA device to determine if there's any systematic offset. Okay, so here's my QA device. Remember to keep it straight. I've taken a measurement. Here's the end of my active source. Here's the end of my dummy. There was a 1 millimeter difference. If they exactly agreed, if my dummy went to the exact same position as my active source, then it would be quite easy. Wherever the dummy ends, that's where the active source would be. But in this case, there's a 1 millimeter difference, so I would need to account for that in my measurements. Here I've got a portable X-ray that I borrowed from diagnostic imaging. I've as straight of a transfer tube as possible. I've taped the center, I've centered on the detector, my ring, taped it down with no gap. Try to keep it as straight as possible. Large SSD minimizes the magnification factor of the source and the detector. So keep it far away. Don't put the imager like right here. And that's about it, about how to take those X-rays. And we'll get into a few more of those details in just a second. One little tip, and this probably should have been earlier in the presentation, but if you remember drawing those lines through the dwell positions on the ring commissioning, that can be a little tricky. Here's a little helpful tip that I'm just going to share with you about how to really get precise with these measurements.
I think we hear the audio. Maybe you can narrate.
Okay, sure. Thanks, Ben. So what I'm saying here is, let me bring it back. So this represents the exposure. Let's say I'm commissioning a tandem, something simple, and I put the end of the tandem tip here. I do an autoradiograph. It creates an exposure when I put this dwell position there for, say, a second. And then how do I find the center of that? What's the best way of doing it? So if I put a rule down and I try to draw a line through it, it's going to be a little bit difficult to tell where to put it, right? I don't know if I'm quite centered on that exposure or not. And 1 millimeter difference can be significant. So a good way of doing it, just draw a quick line on a piece of paper, and then on your Gammamed film, you can see through it. And now you can quickly and easily precisely center that exposure on the line. Draw a side. And then you can use your mark, then you can easily use your ruler anywhere to draw it right through those two marks. And you'll see that after doing that, you've got a line that's perfectly centered on your exposure. So in this case, it's quite easy, but when you start getting to rings where you've got lots of dwell positions and things are close to each other and there are lines everywhere on the paper, this is a really good way to be precise about how to exactly split that exposure on your ring measurement. So again, maybe I should move the slide a little bit earlier, but hopefully that's a helpful tip for you all.
Yeah, maybe we can just take a moment and make sure that there's no questions about that, because I think that that's an important process that we're going through here. In addition, there was a question in the chat from Tabark.
Yeah, sure.
Thank you for that question. He was just wondering what the dummy source is actually made of and some clarification on that.
Yeah, sure. So it's probably different between different vendors, exactly what it's made of, but most of the time, at least the physical properties, the external physical properties should be very similar. So the length of the encapsulation should be the same. The weld should be the same to the cable, and the cable should be the same. So it should behave either identically or extremely similar to the active source. And that's the main thing that we're worried about, is just that it behaves the same as it travels through the ring.
Okay, thank you. And then I had another question just about the borrowing the X-ray from radiology, I think that's an important point about the safety that maybe you can expand on, making sure you keep your afterloader in the shielded vault while you're doing these things.
Yeah.
Or any concerns you might have with that, right?
Yeah, sure. So a couple reasons. One, it's good to keep your afterloader in your shielded vault. Second of all, it's a little bit difficult to move your afterloader to a different room because somehow you'd have to move your console to that other room as well. It becomes quite difficult just in terms of networking logistics to do that. So best to keep your afterloader in its room. Just a note on radiation safety, it's also nice to have your afterloader locked to a wall with a chain cable, something like that. But nice to, usually diagnostic will be willing to come over for an hour or so and just help you take a couple images, and then they'll be able to transfer those images to you. But good question.
Thank you.
Should I continue on, or are there any other questions right now related to anything I've discussed?
It looks like you can continue on. Thank you.
So here again, the same images from earlier, but x-rays of a dummy source. Sorry, so these are the x-rays of the actual dummy source. And again, this is a Varian Gammamed IX plus example. So don't use these values or distances as your own. You have to look up in your own manuals of what your distances are, what your physical properties are. But to explain the concept, I'm going to share with you some of the physical distances of a Gammamed system. So here, for a Gammamed IX plus, not necessarily yours, we've got the active sources in red, physical encapsulation is here. So the distance in a Gammamed IX source from the tip of the source to the center of the active dwell is 2.5 millimeters. And so here's our dummy source, X-ray, at one particular distance. I don't know what distance this is. And so we go 2.5 millimeters, and this would be the center of the active source. So to compare to your TPS active source positions. But remember, we had that 1 millimeter difference in our active source and our dummy source. So we need to factor that in. So that's the center of the active source. It would actually be 1.5 millimeters in this case. Remember, when we measured our dummy source was 1 millimeter shorter than our active source. So we need to account for that. So if I go back here, our dummy source went 1 millimeter closer than our active source. We need to account for that. Instead of 2.5 millimeters, it would only be 1.5 millimeters in this case. So just a little bit about the explanation of how you would account for where the center of the active source is in regards to physical geometry of your source encapsulation, as well as any nominal offset between your active source and your dummy source. And so for me, I would be able to take measurements, and from the end, I don't know what these measurements are on here. You can ignore those, but from the end of my dummy source, you could move 1.5 millimeters and then find where the purple TPS source is, find where that center is, and then you could find the difference between those two, and that would be your difference in position, just like we did in autoradiographs. Again, you're looking for position of the active source versus position of the source on the TPS and what that difference is. And this is how you would do it with the dummy. Again, we would write out what these offsets are. And so for a particular dwell position, where it is in TPS, and versus how far different is it in using the dummy source to see where the active source would be. And we would just plot this out. Notice in my explanation, I've got negative. I put a note of what negative means. Note that negative corresponds to an offset of the actual dwell position closer to the tip than the planning system. So this is the same as theory, and this is the same as our autoradiographs. And notice what's pretty cool is I got minus 5.4. That was the same as my autoradiographs from earlier. I did it as, here's another ring, a different ring, which I got a different value, but that ring that we were commissioning, the two rings, minus 5.4, minus 4.6. So between all of the autoradiographs and the two different dummy sources that I use in that type of commissioning, I end up using an offset of -5 millimeters because that seemed to be about the average of these two and close to what the autoradiograph showed as well. So that's what I would use in my planning system. And here it is again from film. I got -5.4 for both of them. And I got -5.4 and -4.6 using the dummy wire. So I used an approximate -5 for an offset for my TPS, again, which we'll explain how to utilize that shortly. So in this particular set of rings, apart from the first few dwell positions, you see where we had only 1 millimeter difference or half a millimeter difference. The dwell positions are shifted 5 millimeters towards the applicator tip relative to the planning system, plus or minus a millimeter. So verification, this is one of the most important steps. So the whole commissioning process, as you can see, is a little bit complicated. So you always want to verify. So the offset value shift towards the tip that accounts for the differences between actual and TPS dwell positions must be verified. So we're going to explain a few different ways that you can create a plan to account for this. But basically, the main point is here in red, follow your commission method of what you think will deliver systematic point A-like loading. So equal dosage distribution on both sides. So whatever option it is that you do for your planning, try to plan something that's equal dose distribution for delivery, and then verify with film that it does indeed deliver symmetrically as intended. Okay, so you can see that. So this is one method which is described in the Varian manuals. They will reconstruct. So here's the inner lumen, and this blue arrow is where it's reconstructed. This is a solid model applicator file. And so dosimetric in the TPS, it looks like this, but to actually deliver it, you'll shift the sources back by that offset that you've created. So in our case, I had a 5 millimeter offset, where remember the dwell positions physically are delivered 5 millimeters closer to the tip than the TPS is saying. So if I create a second delivery plan where I shift all my dwell positions, here in blue, these are my blue dwell positions. If I shift them all 5 millimeters further from the tip, like they are here, so here's a delivery plan. I've shifted everything 5 millimeters further from the tip. When I actually deliver it, they'll be delivered 5 millimeters closer to the tip, just like we showed in commissioning. So here they are in the TPS, but we know that the actual sources are delivering 5 millimeters closer to the tip than in the TPS. So if I have a plan that looks like this, it'll deliver symmetrically. That's what I thought would happen. I took a film to ensure that it actually did happen. So I've got symmetric loading, just like I intended by using a delivery plan as suggested by Varian. There are other methods that you can use to create proper delivery and dosimetry, and we'll describe a couple of those. So one method is extend the initial reconstruction point on the applicator past the end of the ring by the offset determined during commissioning. Note, TPS applicator models will no longer match the imaging using this technique, so care must be taken. So in this example, instead of reconstructing at the inner lumen, we've reconstructed further, for example, 5 millimeters as the case that I commissioned. This ring may behave differently, maybe it's 3 millimeters, but whatever it is that you've commissioned. By the offset determining commissioning, whatever that offset might be, it won't necessarily be 5 millimeters. Now the TPS applicator model will now not match the applicator image in the TPS. So here's another quick video I'll show you, which tries to explain some of this. So again, this is the delivery of a backward stepping ring. And so here we've reconstructed the ring properly. Right. So the arrow shows the edge reconstructed at the edge of the inner lumen. And the source moves around that path length. And we've loaded dwell positions in the blue symmetrically on both sides. Ovoid-like loading. It's a little bit smaller dose just because the sources are exiting the plane right there. Doesn't have anything to do with symmetry. It's just a little bit difference in source path. So we would do the dosimetry like this in the plan. So this is the varying method from the manual. So this is our plan. And then whatever our offset is from commissioning, then we apply that offset. You can see the blue is going to move shortly. Now I just applied that 5mm offset that I commissioned. It's moved. But if we actually delivered it on the patient, the dose distribution in the patient would look like this, 5mm closer to the distal end. So there's a delivery plan. And this is the dosimetry plan in TPS. It's a little bit complicated. That's why it's important to practice this and use autoradiographs. So one other option, I'm going to pause this briefly. So if instead of reconstructing here, looking at dose distribution in a patient on the TPS, and then shifting everything 5mm back and delivering that plan, you could reconstruct this tip 5mm further. Say reconstruct the tip here, and then plan with your dwell positions. Don't use your first 5mm of dwell positions as we've commissioned, and then your isodose lines in your plan would actually look the same as what's actually delivered to the patient. So again, two different methods that you can do. Practice it. Again, verification. Use an autoradiograph. Whatever method you decide to use, deliver it. What you think will be a symmetric delivery to the patient, deliver that on film and make sure that it is indeed symmetric. That's the most important point for you to do.
Hey, Adam, it looks like we have a question from Ben.
Sure.
Yeah, hey Adam, between the first method and the second method, is there one that you would recommend?
I've gone back and forth between those, and I've discussed with my colleagues, and they've had different comfort levels. Some of my colleagues have liked to use the applicator library, so they can exactly match to the patient. So they've used that approach where they've had the dosimetry plan and then a second delivery plan. Other colleagues of mine have preferred just doing the reconstruction themselves, that offset past where the model applicator file falls. And then you only have one plan. Your dosimetry plan is your delivery plan. It's just a little bit more time consuming to actually reconstruct the ring. So both options are good. Different people have different preferences. Again, choose the method that you want, and important, make sure you verify with film. Plan a delivery of what you think is symmetric loading, deliver it to film and make sure it is symmetric. That's the most important step for whether it's step backwards or step forward rings. Make sure that what you think you're delivering is what you're delivering, because it's complicated. Good question, Ben.
Yeah, and could you show the previous slide? So I'm not a physicist, but I think I understand what you're saying. And if we do the first method, is it as simple as doing the planning like we would normally do, make sure it looks nice and symmetric.
Yeah.
And then making sure that in that plan, we didn't use that first dwell position for like a backward stepper, because that's going to be a little bit wrong.
Correct.
But we used the other steppers in it.
Yeah.
And then just shifting it by whatever measured amount we knew the offset to be.
Exactly. So if, for example, all these dwell positions, the delivery plan, so if this was dwell position, let's say 1270, whatever that is, I don't know what it is, then this dwell position, in order for it to be here in the patient anatomy, instead of the dosimetry plan that has this dwell position is 1270, the delivery would have this exact dwell position at 1265. So a 1265 dwell position would actually deliver in the patient where this TPS dwell position is. So for example, in the varying Gammamed system in Brachyvision, you can just quickly type in a 5mm offset and it will shift all of these dwell positions 5mm further back. So the actual listed dwell positions would be 5mm different than your dosimetry dwell positions.
And do you verify the treatment plan for every brachy treatment?
Yes. So this method, both methods have some complications to them. definitely. So if it's a little too weird with the dosimetry plan and the delivery plan, a nice way is just extending this reconstruction point by that offset amount further. In our case, it was 5 millimeters. And then whatever you plan, you deliver. And so your dosimetry looks like what you deliver. As long as you don't use those first, however much you commission. In our case, we can't use the first 5 millimeters of dwell positions, but you might commission it differently. For your system, it might be you can't use the first 3 millimeters of dwell positions, and you have a 3 millimeter offset. Correct reasoning, Ben. Okay, I'll try and get through this a little quickly. I know we're running long on time. So I've described this dosimetry plan and delivery plan. This will be in the variant manual. Cannot use any of the dwell positions that exist during the tightening phase. So those are those first few dwell positions, maybe where it's just tightening, but the ring's not moving much. For these dwell positions, the actual step size does not agree with the step size in TPS and cannot be corrected for. The dwell positions that you cannot use in treatment planning are determined during applicator commissioning. So again, in our case, it's the first 5 millimeters of step sizes. Okay, so that's about stepping backwards. The stepping forward portion is much quicker, so it'll only take me about 10 minutes. Sorry, I'm running about 10 minutes over. Again, all the principles of imaging with a dummy, looking at the nominal offset between the dummy and an actual source, using autoradiographs, all these commissioning principles are the same for stepping forward systems. So all I'm going to describe is a little bit of the mechanism for stepping forward. So a quick poll question, and then we'll move on. So your department has a backward stepping source system. When using a ring applicator, why shouldn't you use the first few dwell positions at the tip?
Okay, so I launched that poll question, so you guys can take a couple seconds to get some answers. We'll wait around. I want to make sure that we get to this question in the chat. Adam, I don't know if you're going to talk about it in the later slides. There's a really good question from Rebecca about what are the most common errors to watch for when commissioning ring applicators.
Yeah.
So we can wait till the end if you want, or maybe after this poll question if you think it's an appropriate time to answer.
Okay, sure, thanks.
We're at about 40 responses, so we'll give it another maybe 10 seconds.
And remember, we don't see who you are answering, so it's anonymous, and it's not about a right or wrong answer. It just helps us for teaching and seeing where we might have some improvements to make. So don't worry about getting it wrong. I'm sure the educators, including myself, will get a number of these questions wrong, if we were in the audience and having to answer. So no pressure at all.
Yeah, so feel free to just take a guess if you're not certain. We'll end this poll in about 5 seconds because it looks like we got more than half of the people responding, so it's pretty good.
Yeah, great. Well, thanks to everyone. We can end the poll now. You want to end it, Tim? And great. So most of you got it right. The answer is D, because the step size isn't as accurate as these dwell positions. So about the pitfalls, the biggest problems in it. Again, it's a complicated process. I think the biggest errors would be in going from your commission data, so wherever you find those dwell position differences to be, and then trying to figure out how to apply those in your TPS to make sure that they're delivered appropriately. So there are a couple somewhat confusing methods, right? You got the dosimetry plan and delivery plan, and you've also got the extending the length. Then you've got those initial first few millimeters to 5 millimeters or 6 millimeters or so, whatever you determine during commissioning, where you can't use those dwell positions at the very tip. And so trying this, and you can try different patterns and trying to see if you recreate what you expect on film, that is the biggest importance. And so I think that trying to figure out how to actually deliver it to the patient, that's the trickiest component. And so again, that verification, I urge all of you, if you have rings, to try and verify that what you're delivering, what you think you're delivering, is what you're delivering. Let's move on quickly to forward stepping systems. Again, I'll try and do this pretty quickly. Thank you all for your patience and time. As the source steps forward in the ring, it travels in a straight line until it hits the side of the lumen. It then slides along the outer edge of the lumen as it moves around the ring. About halfway around the ring, the source cable kicks out, causing the source to move very little over several source steps. The source is then pushed by the cable around the outer edge of the lumen to its most distal dwell position. So here's a great video. and up. You see it kick out. Let's watch the video again. It's a great video. And right when it gets there, it kicks out. There's friction as it sort of tries to turn around to go the other direction in the ring. And we've got an image showing as it hits this part of the ring, it kicks out. So it starts here and it really kicks out. So once it gets to this portion of the ring, a lot of the dwell positions at that point are going towards the ring kicking out because of friction before it starts moving again along the ring. So it behaves differently than stepping backward systems where it contracts. This one kicks out. And so you've got blue is the central pathway of the ring, and red is where the source actually travels. So you can see the source travel. Here you can see where the different dwell positions are just sort of stuck at one position as the cable kicks out, and then it proceeds to go around the rest of the ring. Okay, so again, you've got this issue with variable step size. You can see the difference in source path for two different ring diameters. They behave differently. Plastic ring versus metal ring. The source runs along the superior edge of the lumen in a plastic ring and closer to the center of the lumen in a metal ring. The exact motion of the source is dependent on source, applicator, step size, similar to Gammamed, or similar to the stepping backward systems. It depends on a number of variables. So flexitron, here's a 1 millimeter step size. Microselectron, 2.5 millimeter step size. And it's funny, you look at these red dots where the source actually goes, and it's tough to see. You'd think, okay, this looks like it's pretty symmetric positions. I don't see any issue. I can just deliver. No, it's very subtle, but by the time you get, if you reconstruct properly on this side, you might have a 5 millimeter offset on this side. So it's sort of tough to visualize, and that's why this commissioning process is so important. So Elekta has an applicator library that has applicator models that accurately track the source path as it moves through the applicator. So even more advanced than the variant system. It has a model that actually shows where the dwell positions are, but you need to buy this license to use it. Now, the process of not using a model file is a little bit complicated and it's tricky. So I've convinced Elekta in the past to give users this model for ring files because it becomes a safety issue. So if you don't have the license for your rings, ask the vendor to provide them for you. If the vendor doesn't give them to you, you can ask RCC for assistance and maybe we can convince them to give you the model files at least for your ring applicators. And we'll explain a few concepts here. So here which one is it? Red. So the applicator model source positions are in red. So this is where the source would actually be. And in pink, we've got manually reconstructed source positions in pink. So this is manually reconstructed. And so you can see on this side, they agree pretty well, but by the time you get to this side, they're really different. Okay, so manually reconstructed with equal step sizes, they become really different. The model file has variable step sizes in Elekta. So you can see it's sort of tough to tell that the red is variable step size, but it really is. You can see the pink is fixed step size. The red is variable to account for this friction here, which causes not much movement of the source at this position before it moves forward. Okay, so you can have big differences if you just manually reconstruct. As part of applicator commissioning, you need to determine what actual dwell positions correspond to the dwell positions you commonly use to treat with. So in this example, so red is the model applicator file, which has the variable step sizes. And pink, you can see that the user has created different step sizes or different positions that if delivered would end up right where that red is. This is really complicated. It's not intuitive. It's not something that's recommended. It is possible. This would have lots of commissioning involved, lots of verification involved. Or let's see, So not only is it important to determine the distance from the inner lumen to the first dwell position, as with all applicators, but you also need to determine location of the clinically relevant dwell positions. The commissioning process itself, like I said, is much like backward stepping systems. You can use an autoradiograph or you can use a dummy wire. But again, that concept is really difficult, not recommended, but it is possible. Again, you would end up with two plans, just like Varian, a plan with accurate dosimetry. Here's the dosimetry plan. Then you'd have a delivery plan, which would look weird on the TPS, but this delivered dwell position, this dwell position, the TPS would actually be delivered here. This one would actually be delivered here. So similar concept to the Varian, but you're sort of commissioning individual dwell position offsets and using those in your TPS. Really complicated, but it is possible. The other option would be to sort of split the difference. So a 5 millimeter offset, okay, it agrees on this side, it's way off on this side. I wouldn't recommend that for this system. A 0 millimeter offset, it's good on this side, and then it goes through this friction and issues, it changes path, and then it's not good on this side. That's not really recommended. Again, this is an iterative commissioning process. In this particular case, a 2 millimeter offset, I want to remind you that these are offsets and distances. In this example, it may not agree with your planning systems. This is for you to commission. But in this example, a 2 millimeter offset is pretty close on this side and pretty close on this side. It sort of splits the difference. So this is the optimal offset in this person's planning system if they didn't have model applicator files to sort of get close along the whole length of the applicator. Okay, again, it's a little bit difficult, similar in concept to the Gammamed system. So your department has a forward stepping source system. Where in the ring do you get a series of dwell positions that are basically on top of each other? Does this happen? This is where the friction happens and the source is supposed to be moving, but because of friction, it doesn't move very much. Where does this happen? At the tip of the ring, at the end of the lumen, about halfway around the ring, at the very end of the ring, or there is nowhere in the ring where the dwell positions are on top of each other. Again, don't worry about right or wrong. This is talking about where we're having variable step size. Give it about 20 more seconds. Feel free to answer. Again, it's a tough question, so don't worry if you get it wrong. Okay, I think that's pretty good, Tim. We can close the poll. And as I'm looking at the answers, I think maybe the question might be a bit ambiguous. There might be some confusion on what I'm actually asking. So a lot of people answered D. There's nowhere in the ring where dwell positions are on top of each other. I think maybe people are answering this question because of, so the correct answer is B, halfway around the ring. So I'll explain the reasoning of this question. So yeah, D might sound like the right answer, and so that's okay. I think it's just maybe poor wording on our end. That yeah, the dwell positions don't necessarily agree with the TPS dwell positions. I think that's why a lot of people answered D. So that's correct reasoning. But what we were looking for is this concept of here. So as it moves around, all of a sudden it gets stuck here for a second as it bows out and due to friction, and that's where you get this variable step size, right? So it moves around the red or the active dwell positions, it comes here, it gets stuck as the wire bows out, that's where the motion is going, and a number of dwell positions are all on top of each other, and then it begins to move around the ring again. And it's this area of friction is why we've got variable step sizes in stepping forward systems. Caution, even with electronucleotron applicator models, you must always verify the source path of your applicator and your source afterloader as part of the applicator and or afterloader commissioning. So they'll give you the models where the exactly, so you can use their models and you plan it, it will have the dosimetry will be exactly like delivered because the nucleotron electa applicator models show the actual variable source positions within your applicator, but you still need to commission it and verify it. Okay, that's important with everything. And all applicators, sources, and afterloaders will behave slightly differently to each other. And some references. you.